Section 8.4, the binomial theorem. The binomial theorem says for any positive integer n and numbers a and b, a plus b to the power n is the same as n choose 0, or this is our combination notation, times a to the n power, plus n choose 1, or again, combination of n elements taken one at a time, times a to the n minus 1 power, b to the 1 power, plus n choose 2, times a to the n minus 2 power, times b squared, plus dot 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 all your middle terms, to the n choose n minus 1 times a to the first, b to the n minus 1 power, plus n choose n, basically a to the 0 power, b to the n power. Now that looks a little bit confusing with all these letters. Let's try it with some actual numerical terms. Exercise 1, we want to expand 2x plus 1 to power 4. Okay, well, using the binomial theorem here, our a is 2x. Right, that's our first term. What we have right there. And our b is 1, or our second term. That's what we have here. So using this binomial theorem, we should have n choose 0. Well, our n is our power, which is 4. What we have here. Okay, so for us, n is 4. So n choose 0 really says 4 choose 0. And then a to the power n is 2x to the power 4. Plus n choose 1, for us that's 4 choose 1. A to the n minus 1, or 2x to the 3, that's 4 minus 1, times b to the first power, well for us that's just 1. Plus 4 choose 2, so notice the number on the bottom is getting larger. The powers of our a terms are decreasing by 1, so now I have 2x to power 2, and the power on our b term is increasing by 1, so I have 1 to the power 2. Now I have 4 choose 3, again increasing. The power on my a term is going to decrease. The power on my b term is going to increase. And then I end with 4 choose 4. I now have my a term to power 0, which is why you don't see it, because power 0 here would make it equal to 1. So that one's basically gone, and I'm just left with my b to power 4. Now you want to evaluate 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And in section 3, I made you do this by hand, but there is actually a way to calculate this on your calculator. Okay, this is not ideal to just show a picture of a calculator, but if you have this particular calculator, which I use in class all the time, what you can do is you can click this button here, this probability button, and a bunch of different options will come up. So let me just write on the screen what it looks like. You'll have NPR come up, NCR come up, and a factorial come up. And then you can just scroll over using your arrow key to the one that you want, and then you can hit enter. So if you were actually typing in a problem, let's say you wanted to write, well, the one we're going to do, which is 4 choose 0. What you do is you would click 4, then you would click probability, and those options would come up. And you're going to scroll over until you're underneath this option, then hit enter. So now what you're going to see is 4, and then you're going to see that NCR, and then you can click 0, so it'll say 0, and then when you click enter, you'll get back the answer, which is just 1. So there is a way to do it on your calculator. Other calculators have this function as well. Sometimes you'll just have a button on your calculator that says NPR or NCR. So again, you just type in your number and then click that button and then click the next number you need and it'll work. You could also go online and do this. For example, you could go use the Desmos scientific calculator. I know we've used the Desmos graphing utility, but you could also just Google Desmos scientific calculator. And that will take you to this site, which looks like this. And you can type in the same problem. So Right here, you don't see that NPR or NCR, but if you click the function button, you'll see them come up. So you can do that. It'll give you your parentheses. You can type in what you need, and it'll give you the answer. Now we're doing a combination, happens to be the same when you're just choosing one. But we could figure out maybe 4 choose 1. Or I'm sorry, the last problem was 4 choose 0. Or you could do 4 choose 2, 4 choose 3, and you can see that we're getting all the different ones we need for our binomial expansion. So use whatever works best for you. You can use your calculator, you can do it by hand, or you can utilize like a scientific calculator online. Okay, so we basically got back these answers. So for 4 choose 0, that was equal to 1. 4 choose 1 was 4. 4 choose 2 was 6. 4 choose 3 was 4. And I don't think I showed 4 choose 4, but it's also 1. Just think, if you have 4 items and you need to choose all of them, then there's only one way that you can take all of them. Or over here, if you have 4 items and you can't choose any of them, there's only one way that you can choose none of them, and it's to choose none of them. Okay, now 2x to the power 4. You got to do the 2 to the power 4, which is 16, and the x to the power 4. 2 to the power 3, which is 8, and the x to the power 3. And then 1 to power 1 is just 1. 2 to power 2 is 4, x to power 2, 1 to power 2, 2 to power 1, x to power 1, 1 to power 3, and 1 to power 4. And now we can simplify. So 1 times 16 is still just 16, x to the 4th. 4 times 8 times 1 is 32, x cubed. 6 times 4 is 24, x squared. I have that 1 as well. 4 times 2 times 1 is 8, x, and 1 times 1 is 1. Now this may have seemed like a lot of work, but you could see that if your binomial was to a high enough power, this would actually save you so much time. Even just doing power of 4, you would have had to basically multiply out this binomial 4 times. So you'd have to do a whole bunch of foiling and distribution and then combining like terms to get to here. So it really is helpful in saving time as long as you know how to compute your combinations. Another helpful tool for expanding your binomials is called Pascal's triangle. And basically, it's a triangular arrangement of numbers that will give you the coefficients in your expansion for any binomial expression. Okay, so here's how Pascal's triangle works. Basically, you start with a 1. And then underneath that, you put 2 more 1s on the outsides. And the sides of our triangles are always going to be 1s. And these are the coefficients that we're going to get in our expansion of our binomial expression a plus b to power n. The next one, you start with your 1, and then you take these two terms and you add them together to get the term in the window. I usually call it a window when it's like between. So 1 plus 1 gives us 2 in that gap. And then on the edges, you always have 1. Again, put a 1. 1 plus 2 gives us a 3. 2 plus 1 gives us 3. And then again, we have a 1. Continuing, we have a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we end with a 1. And you can just keep doing this pattern basically as long as you want. And so on. Now, what does this actually refer to? So this first row here, where we just have a 1, is referring to the coefficient for our binomial expansion of a plus b to power 0, which is just 1. The second one here are going to be our coefficients for the expansion of a plus b to power 1. If it's power 1, then I really just have what's inside, which is a plus b. And notice the coefficient of a is 1, and the coefficient of b is 1. The next one is for the expansion of a plus b to power 2, which, if you remember, is a squared plus 2ab plus b squared. So notice again, the coefficients are 1, 2, and 1. And we just keep up this pattern all the way down. Also take note that I have the same phenomenon with my powers that I had from the binomial theorem above. So I start with power n, which in this case is 4, and then it goes down 1, up 1, down 1, up 1, down 1, up 1, until my second term is now at power n, or in this case 4. Okay, so what we see is that this triangle is used to efficiently compute the binomial coefficients. Let's use that triangle above to expand the following. So starting with part A, so this is power 3. So if we go back up to the chart, a to the third power is going to technically be the fourth row, because remember the first one is for power 0. So we're in this row here. So our binomial coefficients are 1, 3, 3, and 1. But our a in this case is 3a. Ignore the fact that it's the same variable, just this was used in talking about the triangle, and this one happens to have an a for our variable. And our b from the triangle expansions above is now -2. So when we expand this, we're going to start with our coefficient, which is 1, times, what we saw above was we always had our a term to power n, which for us is 3. Then we have our next coefficient, which for us is +3. We have our a term down a power, so it'll be power 2. And our b term now comes into play, and it's raised to power 1. Next coefficient, our a term down a power, so now it's power 1. Our b term has gone up a power, so now it's power 2. And our last coefficient, so we have our a term down a power, which is power 0, so we really don't need to actually write that. So I'm actually going to erase it, because 3a to power 0 is just 1. So then all I really need is my b term up a power, so power 3. And now let's simplify this. So this is 1 times 3 to power 3, which is 27, a to the power 3, plus 3 times 3 squared, which is 9, a squared, times -2, plus 3 times 3 to power 1, that's just 3, a, and -2 to power 2 is 4, and then -2 to power 3 is -8. Simplifying further, we have 27a cubed minus 54a squared plus 36a minus 8. Why don't you try part B on your own? And notice this binomial is raised to power 6. And I didn't put that in the triangle, so you'll need to do one more row of the triangle before you expand the binomial. Again, try this one on your own and then come back and check your work. then you should end up with x to the 6th plus 12x to the 5th y plus 60x to the 4th y squared plus 160x to the 3rd y to the 3rd plus 240x squared y to the 4th plus 192x y to the 5th plus 64y to the 6th.